Okay, so we can also have this session available for people that's not here right now. So back to this, this summary of the tools that we have available. The variant, well, the variant is just who wrote the simulation and what is the dimensionality. These are some of the, also whether or not they can take into account anisotropy. So if it matters what you set the perpendicular resistivity to be, and if they can take into account dipping.
Yeah. Can we get a copy of that table, Joachim?
Yeah.
Joachim?
Yes.
That's it's a brilliant table because I can never remember
yeah,
what half those things are.
Are you sharing a screen? Because I don't see any screen.
Let me. Yeah, let me make sure I'm sharing. Having PowerPoint in full screen and sharing can get complicated. All right, so this is the table. Now you see the table, right? Am I in presentation view or am I?
No, it looks good.
It looks good. Okay.
Yeah.
Yeah. Okay. So this is the table that I was talking about, and yes, I don't think we put it in the workshop materials, but we should put it there, and I'm gonna send it to you specifically, George.
Yeah. Yeah. Sorry to keep interrupting you.
No, what we want. We want this to be as interactive as possible. So.
Okay. And my next question would be, if you can't find the tool that you're looking for, I presume it's the UT Longhorn simulations then that you want to try and find. Is that right? Or
so in this case, for resistivity, we don't have a generic UT tool.
Okay.
They have a lot more variation. However,
okay.
we do have UT. It's called generic induction, and I don't think we have it here.
Yeah.
So
it is here, right here. And this one is not specific to any tool, but you can modify it, and I'm gonna show you. So this is a good. Let's dive right into it. So I'm gonna start with a new well, and we're gonna look into the simulations. And by the way, you can rename any well. You can say properties, and because we're gonna be working with resistivity, we're gonna be working with resistivity in layers. So I'm gonna rename it that. But you can give, and all the wells, you can give them different names. You can also put this extra information. And let's look into the resistivity tools. And we have that generic induction tool that we were talking about. And it's always 2D, and I'll go back to what 2D means in a minute. And you specify the setup here. So in principle, if you know the setup of your tool, you can use it.
Okay.
It's not too difficult to know the setup. You can either find them online or you can ask for it and they'll give it to you. It's not too difficult to get.
Okay. And for an LWD tool,
for an LWD, if it's not induction, you mean, right?
No, yeah, it's not induction. It's
like we have the
I always use the you've got ARC in there or Ecoscope, yeah. So they're the next closest. It's Baker tools that we run.
I see.
And their tools are called OnTrack or AsiTrack.
Right.
And
yeah, I don't think we have a generic.
Yeah.
We don't.
Yeah.
We have well, for lateral long we do have it, but it's not.
Yeah.
All right. So these are the tools, and you saw that most of them are either 1D or 2D. And what 1D versus 2D means is that they're very different, and it's not as intuitive as it's 1D. So, George, I'm going to mute you for a bit because you sound a little too loud, but you can unmute yourself whenever you want to talk, anytime.
Sorry. Yeah.
That's okay. So the 1D assumes no invasion. Well, 1D simulations cannot take into account invasion. However, they can take into account dipping of the angles. So if you have a horizontal well, you're better off with 1D simulations. They assume no invasion. They can handle the variation of the dipping beds. And assumes all beds have same angle. So yeah, so some of these simulations can actually take into account variation in the dipping. So if the trajectory is going around in making different, well, going in different directions near a layer, it's going to some of them can take it into account directly, but some of them cannot do that. They just assume that all beds are parallel to each other. In that case, what we do is we break the trajectory into segments with the maximum variation, and then we run the simulation without you noticing multiple times, or you will notice that it's running, but it looks like it was one run, and then we stitch back all those simulations together. So 1D is good. In summary, 1D is good for highly deviated wells or cases where you have high dip. Then in 2D, the advantage that you get with 2D is that they can take into account invasion. So if you have an invasion profile, you must use a 2D. But they always assume that the well is completely perpendicular to the layers. So you have that limitation. So you have to know which one you're going to use for the specifics of your project. And similarly, if we see that the angle is varying significantly in the trajectory, we just break the trajectory in multiple sub trajectories and stitch them back together. And they all can take resistivity, electrical permittivity, and magnetic permeability. And well, most of them just take resistivity, and permittivity will have an effect, but very minimal. Not all of them take this one into account. And no other property is taken into account. So in the vast majority of cases, the only thing that is going to affect a resistivity simulation is the resistivity Earth model values that you have. If it's anisotropic, then just the homogeneous, and if sorry, the other way around. If it's anisotropic, the homogeneous and the parallel. Otherwise, just the homogeneous value. That's how resistivity simulations work. So we're gonna run a simulation where we're gonna try to match some log that we get from the field. And in your folder, what we're going to look at is this PDF, the thin beds PDF.
Joaquin,
Gabriel?
just before that, in the table you have shown there are some variants. That's 1D UT SA or 1D UT. What does this SA means, please?
Yeah, SA means semi-analytic. Let me bring that table back up because it's the most popular table. Well, it's actually really, really useful. So, right, most of the simulators that we have from the companies, they will just say that it was developed by service company A, B, or C. But in UT, you have multiple. You may have multiple cases. If it says SA is the semi-analytic version, which is usually the fastest. This was developed by David Pardo, and it's very accurate, very, very fast. So it's probably the simulator that I use the most. Well, of course, it's only for induction tools, and well, there's that big limitation, right? And then you have the UT, which usually means that it's a finite element. If you can always ask, each one of those is different. And then we have another one that I don't think we have put in here, but one of the newer ones for 2D induction, we have mode matching. And I think Bruce made this table before it was available, but now I think ARC, for example, we have now 2D UT LWD mode matching. So you will see in the UT simulators will tell you what is the method that we're using, and it's either semi-analytic or mode matching or a finite element. Those are the three most common cases.
Yeah.
Yep. Okay, so now let's go into the project. I have a new well that I just opened, so try to follow along, and I have the thin beds case. That is what we're gonna work with. I'm gonna make this, well, now this is big enough because otherwise I don't have enough room. This should be fine. And now I am going to start by loading the LAS that we need. It's in the same folder that you're using. Everything's in that same folder. So I just go here, load logs from file, click here again, and it's the thin beds resistivity, this one right here. And I can see the logs, I can see the units, and I just say import. And now I see the gamma ray down here, and we're gonna play with this. So the first thing we want to do is see what we got. So I'm just double clicking here to plot gamma ray. I'm just doing it with a mnemonic group. You can do it with whatever. And I'm gonna use that green is a little too green, but so I'm gonna use another better green. It's from 0 to 30. Maybe I'll change the limits a little bit to make it look a little better. Then I'm going to add another track where we are going to see the resistivity itself. And I am going to plot the boundaries and the resistivity. That is, in this case, is going to be RT90. So I select LAS and then RT90, or I could go with mnemonics and alternatively mnemonics and deep resistivity. And it already has it. Now, of course, we prefer to see this in logarithmic scale. And because I know what it's going to look like, I'm going to go from 3. I just changed the left limit to 3. 3 and 3 decades is fine, and the left offset 3 is fine. So it's going to go from 3 to 3000. And by the way, notice there's here in the legends in the top, you can right click on them, and there's hide, delete. There's a number of things you can do here. Also, you can move things around if you drag it from one track to the other. It's an easy way to do that. And you can also, if you right click when you drag, it doesn't just move it, it copies whichever plot you're working on. Just, it might be useful in some cases, just little things that might be helpful at some point. So now we have, these are the 2 main logs that we're going to be working with. We can see very clearly that there's thin layers. By the way, sometimes people complain that this looks a little absurd, but it's actually based in real cases. You can see these laminations. Now, what we're gonna do is the first thing is we're gonna define the boundaries, and again we could do it manually, but let's save some time by using the text boundaries. And in this case, we're gonna use gamma ray. And just to make it a little different, let's do it with both, because we can see they are pretty close, and there might be some features that are in resistivity but not in gamma ray. Let's add them both. So I'm gonna do gamma ray and RT90, and I'm gonna use maximum variance. Let's see. maximum variance and 1 and 0.1, and let's see what do we get. Well, it's actually not bad at all. So I'm just going to keep that and refine it manually. And by the way, the limits, the modeling limits, just to make it, just to be more focused on the area where we actually have data, I'm going to change them to 5,000 to 5,050 feet. And okay. Now the limits are just where we have data. And remember, you get the magnifying glass and you double click and it zooms into the modeling limits, to the modeling interval. Now we have both plots and we have the boundaries. Now, it's not a good idea to have too many. So I'm going to remove some that I think are unnecessary, and I'm gonna try to put this. I'm also gonna shift them to the positions where I think they're gonna be better. If you have too many, you're gonna be missing some shoulder bed effects. So that's why it's not always a great idea to have too many. I'm getting rid of some of them. And when we do the inversion, it's gonna be heavily dependent on the locations that we use. So at some point, it's you will be refining them, not just like I'm doing right now, just guided by the log itself, but by how closely can the log be reproduced by the simulator. So it becomes like a double situation. So now that's it. I'm going to leave it like that, and we'll see if I need to modify it later. Is everybody over here? Does anybody has questions or got stuck somewhere? It's okay. All right, well, I'm going to delete this one too. So now that we have done this, I'm going to run the simulator. In this case is AIT. I'm going to use the 2D Schlumberger. If you don't have the AIT, if you don't have the Schlumberger NDA, you can use the DLL. It's not exactly the same, but it's close enough. Use the 2D UT mode matching. And it's going to be okay. You're going to get slightly different results, but the point is the same. And is the AIT-H model for this tool. And there's no extra inputs. It's just 2D and that's it. Then here we can choose what is the name of the output and if we want to close the command window on completion or not. This is more well, if I say don't close, whenever I run the simulation, I get this extra window and there's some information here that can be useful sometimes, especially when the simulation is not running as expected. You may get some extra information here. So that's why we have that option. But in most cases, I'm just going to close it because otherwise I end up having too many windows there. And now that I've done that, I'm going to plot that simulation. But that simulation is going to be is based on the Earth model. So I'm going to first plot the Earth model. So it's going to be Earth model, resistivity. And parallel or homogeneous. And you can see that everything is back there. I'm just going to change the color just because I think it's easier. And I am going to add also the simulation. So now notice we also have simulated log as type because we ran that simulation and we only have this one log set. And RT90 is the log that we had. So I'm going to put it there. I'm going to change the color to blue. And in general, for all the simulations, I tend to use dashed lines just because in my brain that tells me that that was a simulation. it's just easier to remember if you're consistent with these things. So I always do dashed. Now you can see that well, it's nowhere near the log because, well, we didn't give it any information from the log, so we would be silly to expect that it's close to it. It's just taking the information that we got from the default. So to improve this, we could just manually modify the resistivity and simulate, and you would see that at the end of the simulation, it gets updated and it's closer to it, but it's still very far. So something we can do to improve this even more is to do the populate properties, what we've done before. And resistivity is going to be set up as RT90. And if I say populate, takes a second, and all the resistivities are in RT90, but of course I didn't set up the same limits, so they're quite off. So for the Earth model, well, I'm going to right click here in the RT90, the one that I got from the field that goes from 3 to 3000, and I'm going to say snap all the logs that have these units into this RT90 limits. So now we see that the Earth model properties are following the pattern that we wanted to follow, but the simulation is really far. So now I run simulation again, and now it's a lot closer, but it's still not reproducing it perfectly. Now, something that I like doing here is to get a bit of a metric of how close are we. So in the track editor, I double click here to get the track editor. By the way, if I'm going too fast, just stop me at any point. Now we have the track editor, and I'm going to add a shade plot. And the shade plot is in between, well, I can choose which curves I want to use. So I'm going to use the RT90 from the field and RT90 from the simulation. And you have two colors, you can put them both. And right here, you're going to see that you get an RMSD, a root mean square deviation. That gives you an idea of how far or how close you are from being right. And whenever, for example, I can see that clearly this value needs to be modified to the right. So if I move it to the right and hit simulate, I am getting closer, and it went down by a minimal amount, but it did go down. So this was 16.73, and then let's see, 1668. So it's very, very minimal, but it's getting better. And is everybody here? So far?
Yes.
Yes. Okay. Good. Very good. No questions, no comments?
Joaquin, so in the point we had already set the equation for this saturation, or did we not do that?
We did not do anything in that regard. At this point, we're only trying to refine resistivity itself, which afterwards can be used to calculate saturation. So we're going backwards. We're going from the field log that we got, trying to get the composition. Well, first today we're just going to try to get the resistivity itself.
Okay, and at this point we have done only direct simulation. We haven't done inversion yet, right? That's right.
That's right. We're only doing forward simulation, and we're doing some manual inversion, quote unquote, by just modifying the values of the resistivity at these points, just to try to reduce the RMSD, to try to get a better match, because we can see that clearly it's the resistivity is being underrepresented in most of these cases. So you can try to do that manually. And for a while, this was the only option that we had. Now I got it to 12 by those modifications. But now we have an automated way of doing it, which is before we used to spend like an hour with everybody trying to do this by hand, and we would try to get a competition, and Roger would always beat everyone because he has done it too many times. But now we have MCMC, so let's use MCMC to try to do this.
Thank you. Perfect.
So we open this MCMC module, the Markov-chain Monte Carlo. I'm going to move this over here. And we're going to go through the whole thing so to understand what's going on. First, the property that we're trying to invert for is resistivity. So make sure you have resistivity here. Then to make sure that the values that you get are reasonable, you can give it a minimum and a maximum. In most cases, they don't matter too much, but if you have a hard limit, it's important that you do that. Then in some cases, for resistivity, maybe not so much, but for other properties, you may have core data that is very narrow, that narrows down your result, and you may not have it for the whole thing, only for some of them. What that's going to do is if you have some core data and only in some of these layers, let's say this layer, you have some core data that says that resistivity or whatever property it is has to be here, it's going to fix the value for this layer at that point, forcing the neighboring layers to improve their match with that condition. Because of course there's shoulder bed effect, so the neighboring layers will have to take that into account. And then the zones that you want to determine, this only matters if you're working with 2D. In this case, because it's 1D, it doesn't matter. And the tool that we're going to use, we have to make sure we have the same. So it's AIT, and we're doing the 2D, and it's AITH. And remember, DLL lateral log if you don't have Schellenberger. And then you have the settings. In this case, there's no, well, it's only whether you take into account relative electrical permittivity or not. But there's not a whole lot of settings here, so it doesn't really make a big difference. And now this is where we say what are we trying to match to what. So the simulated logs that we're going to get it's RT90, and we have the same name here. So just make sure that you're trying to match RT90 to RT90, and we could have more. Just going to add another. In this case, is not the main goal, but you could. I'm going to actually add it in a separate. It's getting a little too busy. So I'm going to move this. And just so we see what happens there. I'm going to add them all, but really it's just I'm going to hide the boundaries. No, in the fourth, I'm going to instead of RT90, we're going to do it with, well, with the shallow resistivity, which is RT10, so that's fine. And let's do the same here. It's RT10, but the simulated. You can see that clearly they are quite different. Again, we prefer logarithmic, 3 to 3000. That's fine. And let's see how this looks. So first, let's do it only with RT90, and then we'll try to match both. So first, just this one. Here's some other options, whether you want to auto update the Earth model. So this is going to be an iterative process. If you have this checked, every time every step is going to be updated, and it looks nice. So I'm going to leave it open. If you want to auto update the log, also let's leave it like that. Right, if you want to see the logs before the fix of the properties are, that's also a possibility. And then we go into the method. We have two methods. We have a biased sampling method and then a quasi-Newton method. they started by being very different, but they've been converging. The quasi-Newton, the biggest difference is that the quasi-Newton works with an approximation of the Jacobian to try to converge a little faster, and the biased sampling approximates the derivative with the difference between the field and the simulated log. Let's stick to biased sampling first. This is a bit of an explanation when it's each one recommended. And then we're going to have two stages when we run this inversion. We're going to have a first stage where we're just going to try to minimize the match between these two, which we call the accelerated search. And then we're going to have a second step where we're going to improve the uncertainty calculations. We're going to focus on uncertainty calculations. Then you have the noise, and 0.03 is fine. That means 3%. You can do either a fraction or an absolute, or fraction plus absolute. That's also fine. The random perturbation, how close do you think you are from the final answer? And some Warhol corrections. That if you have, if you know that some areas or some intervals have issues with the Warhol, if you have washouts or something like that, that you could see they would be reflected in the caliper or in the density delta logs, you would use this section. So let's try to not be overwhelmed and just try to invert for this. So I'm just going to click run and let's see what happens. You're not seeing it, but in my other monitor, I get the pop-up window. Sometimes the first time you try to run it, it doesn't improve at all. It's a little bug, but if you run it again, it will improve. Yeah, it will improve. And you can see that the RMSD is being decreased. Now 9.6, 8. And you can see that the match is nearly perfect. At some point, we're going to see that there are some areas where moving the boundaries a little bit can help more than keep trying to use the same, more than just modifying the property itself. Right now it's 6. I think the lowest we've gotten is like 2 RMSD, pretty low. And it only ran for 10 steps because, well, it went below the RMSD went below 3%. And at that point, it was going to stop. And you can, yeah, if you click in any of these buttons, it tells you what's going on. The misfit here, if you forget what, well, the RMSD is just, it's very simple to calculate. Well, it's just root mean square deviation, which just means that it takes all the points in the simulated versus field, compares them, makes the one minus the other, then square, then add all those squares, and then square root. That's root mean square deviation. That's all it means. Then the misfit is the same thing. You can see that it's the same thing plus this term, that noise term. That noise is coming from here, unless you have Warhol corrections. And so unless you have Warhol corrections, it's going to be uniform for all of them.
Okay, I have a question. This RMSD, root mean square D, is the error of the R, right?
That's right. Yeah.
Not the log R.
Not what? Sorry.
Not the log R. Logarithmic of R.
No. It's not log R. It's just R. That's right.
Okay.
Yeah. For the behind the scenes, the optimization is done in log R because, of course, it's a lot faster. But the numbers that you're seeing are not log R. They are the number itself. So I'm going to make this RMSD. Let's say we're shooting for 0. Of course, we know that's pretty much not possible. And I'm just going to run it for 10 more iterations. And I'm going to run it for more iterations, for 30. And I'm going to allow it to adjust bed boundaries. And you're going to see that as the simulation goes, some of the boundaries are going to start moving a little bit, and that usually helps. That drops the RMSD significantly whenever that's possible. We cannot make miracles, meaning that the moves that you're going to see in the boundaries are local. We don't make boundaries appear, or we don't make big shifts, but it's not too difficult for you to get a good approximation or a good first order approach, and then you let it do the final refinements and tries to get as close as possible. Now we're getting close to below 2. And you can see that really the match between the simulated and the field is pretty much impossible to improve to get any better. And we're seeing also that the mean uncertainty is being calculated and is going up. So we're going to plot it. As soon as this is done, we're going to plot it and we're going to see what's happening with the mean uncertainty. Comments, questions? All right. So I reached 30.
Yeah, okay, I have a question. So after once you do this, do you get the solution answer or a resistivity value and layer essentially Earth model?
That's right.
You can export it by the ASCII file or Laplace file.
That's right. Yeah. So here there's a couple of ways. You can say file, save Earth model to LAS. That's probably the easiest. And you can either use the measured depths of whatever. For example, if this was your field log, maybe you want to save it as having those same measured depths. And I'm not gonna you can convert. This is gonna save the Earth model. You can convert all properties, but that's a lot of properties. So let's just look into resistivity so that it's not too much. And then I can say save. And I'm gonna save it here. It's Earth model for well resistivity thin layers. Save. And now that's the folder that I have here. It's gonna show up in your folders if you download it again. And you can see the LAS file that looks something like this. So it's gonna be the same measured depths that you had with different resistivity values. And you can see there's some repeated. This is 3 of them were the same layer, then this different layer, and so on. So this is one way. This is probably the most standard way. You can also, if you don't want to match that, you can do it with using Earth model blocky logs. And if you do that, it's going to be discontinuous. I'm going to just overwrite it, and you can see how it looks like. Just show me the new one. And that just means that it's discontinuous. So you have one value from this measured depth to this other measured depth. This is basically the first layer. And then from that same measured depth to this other measured depth, you get the second value. So you always get 2 values with pretty much the same measured depth here. There's a small variation just to avoid numerical problems with a real discontinuity. But you could also do that, and you will see the discontinuity if you load it in any other program.
I got a question here. You might have explained it. So what properties has changed to get a match for the resistivity?
The only property that we were working with was resistivity itself.
Yeah, I know. So you simulate the resistivity, right? So you have to have some, I don't know, some fluid properties changing that can get the match for the for the resistivity or other things.
So we have 3 resistivities right now that we're looking at. We have the field resistivity, we have the simulated resistivity, and the Earth model resistivity. This Earth model resistivity in reality is going to depend on your fluids. It's going to depend on the model that you really have. It's going to depend on the shale concentration that you have in all those other things. Now we're skipping that step, and we're just saying, okay, we're only going to care about resistivity on its own, because this is the resistivity that I could use to calculate all those other things that you're thinking of. I can now use this resistivity to calculate saturation, or I can use this resistivity to get water resistivity or porosity, or whatever you want, depending on what you trust more. Tomorrow today we're gonna pretty much finish in MCMC, but tomorrow when we do inversion, we're gonna do first this type of inversion. We're not gonna do it only for resistivity, we're gonna do it for nuclear logs and for other nuclear logs and resistivity. And then we're gonna combine it to try to get the composition. So to try to get all those answers that you're looking for. But this one is just, we're skipping that step. We're assuming that the composition is irrelevant. We know it's not, but at this level, that's what we're assuming. Make sense?
Yeah, okay. So by the way, can you also save this project so later you can share your version of the project, so we can also look at it if it's needed?
Yeah, for sure. Yes.
Yeah, Joaquin, I have a question, follow-up question.
Yeah, I like this question. Good, go ahead.
MCMC inversion you are using to any kind of tool responses. So I understand that you can use RMSD as a criteria, one criteria. But when you are talking about resistivity or permeability, which really changes over the very large amount of, so many decades, then I think it's better to use a ratio of not the difference, but the ratio between the resistivity model and input resistivity output. So that is equivalent to RMS LD. And then that is better for
the ratio, and try to aim for 1.
Yeah, for the resistivity, or conductivity is same, just minus.
Yeah.
And then if you have some simulation to invert involving permeability, it's also
the ratio, and try to make the ratio equal to 1. That's what you say.
Yeah. Well, the result probably doesn't change much for this model, but
right.
Yeah.
No, yeah, that's good. That's important to know. Thank you. And by the way, we don't use RMSD directly. We use misfits. I know potato, but in this case, it wouldn't make a difference because we don't have any Warhol effects. But if we did have Warhol effects, it would make a difference. I'm going to design an example that shows that. But I mean, it's a little too much information to pack in a single session. Okay, yeah, we'll take that. Now, in the resistivity, we can also plot the standard deviation, and you can see, of course, the thinner layers have higher standard deviation. Also, the low resistivity layers don't have a lot. This one, of course, this one is too close to that, so we can ignore that. Well, not ignore, but it has that other effect of this tiny one that is not helping. But all the others look pretty consistent, and that's good. But it's not the final answer. So they just seem to have the right trend, but we're going to try to improve it. Also notice this is just the standard deviation, but we can also see the confidence interval. That personally, I prefer to see the confidence interval because it doesn't only show you the relationship between each other, but it shows you the asymmetry, which I think is very important in this. For example, in this case, the minimum is over here, but the sample is biased in this direction, which is also in this case is artificial because we've been sampling this area. So when let's stop saying but let's actually do it. We're gonna run this. It's not only accelerated search, and we're gonna run only a very short accelerated search, just 10 steps of accelerated search, and then the rest is going to be the out of accelerated search. That just means we're focusing on the calculation of the uncertainties. And you can see, well, I like seeing how the uncertainties evolve as the simulation runs. It seems to be going in the right direction. And when the uncertainty is, you're going to see that the curve here, iterations versus mean uncertainty, at some point is going to stop growing. At first, it's just going to grow. And at some point, it's going to stop doing that. And at that point, you can start assuming that your calculations are correct, or more likely to be correct. So now it's more realistic. Of course, still not stable, but you can see how they're getting more interesting and more interesting. And you see here around 10 iterations, we had that little kink. It was going very, very flatly following a certain direction, but then we switched the search algorithm, and you can see that it has a different trend. When the trend that we expect, which is going an asymptote to a certain mean uncertainty. And they're gonna keep changing, but you can already see the trend that lower resistivity have lower uncertainty, and thinner layers also have higher uncertainty, and that seems correct. They should be even lower than, or at least I think they should be a little lower. Nothing beats the actual measurements, right? But that would be my intuition. I don't know if we have any questions or comments. Complaints also taken. Bruce, anything you want to add? Carlos, something you want to add?
No.
Okay. Well, it's reaching stability. You can see that the mean uncertainty is not going much faster. So I'm going to stop it. And then, well, you can use these values for future analysis or for other things that you might want to do. The other thing I wanted to show you is that we can do, well, let's do it for these two simultaneously, for the shallow and deep. It's just a better match. It's not going to be all that different, but for example, here you see that there's the match is pretty bad, relatively speaking. Let's add the shade plot. And you can see RT10 versus RT10 is higher than this. It's not that higher because they're in this case there's no invasion, so they're following the same trend. But if we run it, hopefully this will go lower. The only problem is that whenever you run it again, you destroy your answers for uncertainty. We may want to look into that. But now you already see that it went lower. Well, I think it just grew. Yeah, RMSD is growing a bit, but and that's because the misfit is going down. And that just means that, well, in this case, it just means that the lower resistivities are getting better match than the higher, and that's okay. Because the noise has a part that is a fraction. If it was just absolute, that would not be possible. But because some of the noise is as a fraction, basically it's saying that the lower resistivity measurements need to be more accurate. And this is what we see in the field, so that's fine. And now we're calculating the uncertainty. You can also see in low confidence interval, I prefer. And they follow pretty much the exact same trend in both cases. But if you have invasion, this will have a much higher relevance. We see, in my experience, in most cases, roughly 50 iterations is enough to get at least a good approximation of the uncertainty. It takes a few minutes, no more than 5. Of course, this depends 100% on the simulation and the forward simulator that you're relying on. This one is pretty fast. All right. I'm just going to stop it. All right. Any more comments or questions? That's it. All right. Well, that's it. Just for bonus, I'm going to do gamma ray. Tomorrow we're going to be doing these a lot, but I just want to see what happens. I haven't done it before. Let's see how close we get. Well, would be good if I plot it. No, I couldn't plot it without at least one simulation. There. Oh, the limits are pretty off. Now we have the limits right. Looks okay. 1 foot is a little too much, so I'm going to make it every half foot. That's the sampling rate for gamma ray. That looks better. I'm going to make a simulated dash just for consistency. And I'm going to plot also the confidence interval. And here I'm running into a problem. I cannot match the ones in the left. And there's a reason why I cannot do that. Can anybody tell me why?
Yeah, the Earth model property is set to 10. Is that it?
Right. Well, the minimum.
Top left.
Yeah.
Yeah, the minimum. Yeah.
Yeah, that's right. So if I make it 2 or something like that, yeah, in this case it needs to be allowed to go below 2. So I was shooting myself in the foot. Now you can see that the match is a lot better. And of course, we expect the uncertainties for gamma ray to be much smaller than for resistivity. Just nature of the beast. And that's it. More questions, George?
Yeah. The uncertainties you're seeing on the resistivity, can we see those as a water saturation as well? An uncertainty in the water saturation?
They will be translated when you do the joint inversion. Yes, but if you just run one single calculation, we don't have that. That's a good idea. Yeah, that's a good idea, of course. But if you do it with a joint inversion, which we will talk about tomorrow morning, yes, you could.
Okay.
All right. Well, that's what we have planned for today. I don't know if there's more questions or comments, or Bruce, do you want to add something? Or
I just want to say, is anybody using the MATLAB-based software, or are y'all using SA? Because tomorrow we're going to be doing some NMR, and if you're using the MATLAB-based, then I want to be sure that you update it with the files that we included in the workshop files. So
is anybody using MATLAB based today?
Or if you plan on using it tomorrow.
I have standalone. So the MCR, no MATLAB.
Okay, that's fine.
All right. Well, then hopefully, I hope for Friday, you'll probably want to have the MATLAB based. I mean, if you want to follow along on the scripting. But otherwise, for tomorrow, the standalone should work fine, if that's all everybody has.
Okay.
All right. Well, thank you guys, and I'm done. And anybody else comments or anything? Otherwise, we can take off. I'll share with you the table, George, and I'll put it in the folder for anybody else who may want it.
Right.
All right.
And this was just the first day, eh? Just the beginner session. Can't wait for tomorrow.
Yeah.
It will be more complicated, George, right?
Yeah. Watch. Be careful what you wish for. Yeah.
Exactly. I
Yeah,
think I was stuck in the second day. For the last time I joined, so we'll see.
Yeah, good. Yeah, I hope it's not too overwhelming, but yeah, it's a crash course.
Yeah, that's good.
All right. Well.
All right. Thank you.
Thank you.
All right.
Have a good night.
Thank you very much. Bye.
Bye.
Well, I'm gonna send those files, and I need to. I'm planning to expand something on the one I'm doing, but otherwise I think that's it.
Okay.
All right. Well,
See you in the morning then.
see you tomorrow in the morning. Bye.
Thank you.